So these are the contents. So signal, what is signal? Signal is the variation of one parameter with respect to one or more independent variables. It can be time or the space, and we listen and touch anything, that's also signal. And temperature or the elevation or the displacement in earthquake or the X-ray, the propagated signal or the transmitted signal or reflected signal can be also all included as a signal. Radio, microwave, and etc. etc. So we are receiving lots of kinds of signals. And one-dimensional signal is what? So when we measure a point, when we do the point measurement, that's a one-dimensional signal, right? So you get the information about that location. So here is the example of the TDR system. And if you push this fork to the ground, the soil specimen, and you measure electromagnetic signal, it gives you the moisture content, right? And that moisture content represents the location of the soil, right? And this is elastic wave source. If you measure water injection, I think that appears. So this gives you the wave velocity or the stiffness of the location. And if we do this kind of measurement along the line, along the space, or the x-axis, or the y-axis, or z-axis, then it gives you the two-dimensional signal. And this is the example of the GPR trace, so that you have a dolly with the electromagnetic propagation and receiving system, and you just roll it along the line that you want to scan it, right? So then you get the spatial information along that axis. You can do it like area scanning or the line scanning, right? If you do the area scanning, then it's just still the two-dimensional signal. And if you get the topographic or the information or along the z-axis or depth axis or along the altitude, then you get the three-dimensional signals, right? So then we'll talk about the systems that transform an input signal into an output signal. So always, this is a kind of an engineering system that we are dealing with all the time. So you have an input, and you have a system, and you have an output, right? And for example, in the Indian Ocean, you have a 9.8 magnitude earthquake, you get the tsunami, right? So this will be the input. Earthquake is the input signal, and the ocean is the system that you may be interested in, and tsunami is the result and output, right? So depending on the engineering problem, you may be interested in this earthquake, or the output, the tsunami, or could be the Indian Ocean, right? So other example will be what? Here, you have a body as a system and stimuli. So if you hit it or hear the hot surface, then you get the response, right? That's the output, right? So we can define any engineering problem with this kind of systematic thinking, the input and system and the output. The building, you have a wind as an input, and you have a building as a system, then you get the oscillation, that's a response. And transducer is, and when we measure the input and the output, we use the sensors. And what is the sensors? Sensors detect the signal, acquires the signal that you can interpret, right? So that gives you the information that we can analyze. So if you have the transducer that transform the mechanical energy to the electrical energy, then you can, let's think about the example, accelerometer. Accelerometer, have you used accelerometer? Anyone? 동아, you used accelerometer, right? So how does it work? 뭘로 바꾸지? Mechanical, electrical. Mechanical energy to voltage, the electrical signal, right? So where there's a vibration, and that transducer transforms the mechanical energy to the electrical energy, Then you see that the electrical energy by using oscilloscope or the digital AD board, right? And for pressure transducer, also when you have a mechanical pressure to the transducer, that transforms the energy to the electrical signal, right? Band elements 2, strain gauges 2. And there's the other way. You can go from electrical energy to the mechanical wave. So for example, speaker, right? You have a electrical signal to the speaker. It's going to be voltage or it can be current, and that gives you the sound wave, right? The outdoor sound. And the earthquake, if you have an earthquake and dam is the system, and you have the vibration mode, so that's another mechanical and to the mechanical or to the electrical energy if you have an accelerometer to measure it. Here is just a picture of the landslide. So here we can think of the slope. The natural slope is the system, and earthquake or the rainfall is the input, and the response was the failure of this slope. Just a simple example. So then, from cause to effect, let's imagine that we have a bottle of this shape so that the water is filled up by this much, and you have a change in diameter as you go to the bottom. And if you open the valve here, and you measure the Q, the rate of discharge, then rate of discharge will vary with time as this water surface goes down, right? And that Q is affected by the area of this bottle, right? And also the height. But the height will be just the dependent variable, right? So so then, what is the input? Input is water height, or we can say water flowing. Then system is this bottle, right? Is the system, and output is discharge rate, the Q, the flow rate, right? So that let's assume that we know the shape of the bottle. So we know the system, and we know the input, how the water flows down. So let's say that we know the physics of the water flow, right? And then can we calculate can you estimate or guess the flow rate, right? And that's called the forward problem, right? So you know the input and you know the system, and you want to find out the output, right? From cause to effect. And you can do the backward, right? So now you have a measurement of the flow rate, and you know the input was the water, and you want to find out the diameter of the bottle, right? Then it's called the inverse problem, or some people say that the back analysis, right? Or some people say the system identification. So because we want to identify the system right now, so we want to know about the system. So then we can define it as forward problem and inverse problem using this kind of a conceptual thinking. For example, system design is we know the input signal and we know the output signal, so that we design the system. It's the system design. Right? And convolution is we know the input and we know the system, so we'll know the response. So that's the forward problem, and it's called convolution. And inverse problem is now we know input and output, and we want to find out what the system is. Right? So then it's going to be the backward problem that we just talked. And the last one is deconvolution. So now we know the system and the output signal, and we want to find the input signal. Right? So for example, Tae-Hyuk is working on the debris flow, right? And debris flow from the Umunsan debris flow. They measure the result of the debris flow. So for example, the velocity of the debris flow or the excavated area of the debris flow. So total amount of the soil volume is measured. Right? And they know how the debris flow flows. So it means that they know the system. And they want to find the input, which is the soil property, right? Or the rheological property. Right? That's the backward problem. What about the earthquake? So geophysicists or the hardcore earth scientists find out the structure of the earth from earthquake signal. Right? So they measure the earthquake signal. And what is the system? System will be the earth, right? Structure of the earth. And input is the earthquake, the PNS wave. So that's another the inverse problem too. Right? So engineering design, the system design is, you know the input and output, and you want to design the system. For example, you have the design load, and you have the design criteria to avoid the failure, and then you do the system design. And convolution is like you have the input parameter. So let's use the numerical simulation as an example. And you know the input parameter, the soil property. And H, you have like dam structure or the geometry of the dam. And you want to find out the flow rate of the dam. Right? So from using this numerical simulation, then Y will be the flow rate. The unknown is the output. So that's convolution problem. And system identification, as we talked before, so you have a pile of this, and you want to find out the shape of this pile, or the drilled shaft, right? And so you hammer, hit the head of the pile using the hammer, and you measure the reflective wave, maybe at the ground, and this is the output, and this is the input, and you're identifying this pile shape, right? So that's the system identification. Tomographic imaging, so it's, I think it's a human lying on the bed, CT scanner, right? And so using this source and the received signal, we want to find out what's inside our body, right? So mainly finding the cancer. Deconvolution. Deconvolution, here we have the example of the earthquake. X is unknown. So let's say we want to find out the location of the earthquake. Right? So then that's going to be deconvolution problem. You have a seismogram and you have an output. Then from the output, we are going to find the location, the source of this earthquake. Determining the source of the pollutant or estimate of initial velocity of a vehicle from a skid mark is also another deconvolution problem. Okay, so then it's your turn. Now let's make an example of any engineering problem that you can think of and find one example for each case, at least. Okay, guys, time's up. So 어디서부터? So who's gonna be the first? 여기서부터? 너희부터? Okay, this group. Okay. So everyone, please listen to them, and they're gonna start first. Okay. So let's start with the system design problem. 아무 말로 하는 거야?
예상되는 강풍이 있고 디자인 크라이테리아를 알고 있을 때 모양을 설계하는.
So bridge design, and the input is wind, and output is what? Design criteria of what? Maybe deflection. Okay. And convolution problem.
시스템은 댐이고요. 강우량 레인폴이 인풋이고 그걸 알 때 워터 볼륨을 예상.
discharge rate, calculation of discharge rate. Okay. And system identification.
그 레이저 쏘는 걸 생각을 했는데 레이저가 인풋이고 그 레이저를 쐈을 때 시그널이 있을 거 아니에요. 그 시그널이 아웃풋이고 그 두 개의 신호를 이용해서 크랙을 찾는.
Okay. Location of crack.
네.
And the deconvolution problem.
시스템은 강우계고 강우계에 측정된 양을 가지고 전체적으로 비가 얼마큼 오는지를 알 수 있어요.
System output is
그 강우계
water height. From that you calculate the rain intensity. Okay. 혹시 comment? Any question? 이상하다 뭔가. Something's wrong? 아니야? Okay. The next group. 지원. their group. System design.
시스템 디자인은 사람 눈이 뭔가 원하는 시력이 있을 때 안경을 맞추는
Design of glass. Glasses. That's
시험 프로그램은 아직 저희가
okay. And then system identification.
시스템 아이덴티피케이션은 인풋이 얼스케이프 있고 아웃풋이 다이나믹 리스폰스가 있을 때 빌딩 시스템의 어떤 구조물 보여주기나 그런 다이나믹 캐릭터리스틱을
Natural frequency of the building is the system identification. Okay. And deconvolution problem.
컨버전 프로그램은 이제 엑스레이 같은 걸 뭔가 아웃풋이 엑스레이를 통한 사진, 영상 사진이라고 하고 어떤 엑스레이 시스템이 있으면 사람의 뭔가 그런 몸의 문제라든지 찾아내는 걸 생각을
That sounds more like system identification. Okay. So deconvolution is to find the source or to find the input information. Yeah? Okay. So no, next back there, Soran's group.
시스템 디자인 같은 경우에는 터널 같은 걸 지을 때 저희가 짓고 난 위치에 따라서 하중이 크기나 이런 것들이 붙이고 그랬을 때 뭐 워크볼트의 양이라든가 콘크리트 두께 같은 것들을 설계해서
Okay. That's the design 이 락볼트 system. Okay. Convolution.
어떤 소일에서 하이드레이트 같은 경우에는 그 서멀한 경우랑 하이드롤릭한 무브먼트랑 메커니컬한 그런 것들을 어떤 해석 프로그램을 이용해서 시뮬레이션 하는 그 하이드레이트가 헤리데스가 어떻게 변하는가 이런 것들을 볼 수 있는 시뮬레이션 컨버전 프로그램.
So the input is what? Input is
soil specification.
soil property, and system is hydraulic bearing sediment, and output is response of the or the pore pressure or strength or something like that. Okay.
시스템 아이덴티피케이션 보월 테스트처럼 어떤 탄성파를 집안에 줬을 때 그 속도가 아웃풋으로 나오게 되면 그에 따라서 현재 그 집안의 인텐시티라든가 이런 걸 시스템에
So it's like a cross tomography using S-wave. So to find the what stiffness profile along the depth, right? That will be the system of the soil. Deconvolution.
아베이나 그런 데브리 플로우라든가 그리고 뭔가 다른 저희가
Okay. Deconvolution is not difficult. Okay. Next group. 여기는
시스템 디자인 프로그램은 처음 공부했던 것 중에 궁금했습니다. 교량 설계할 때 포화준을 가지고 그 설계하는지를 생각하겠습니다. 두 번째 컨버전 프로블럼은 그 각천의 범람 예측이라고 해서 그 인풋을 강우량으로 놓고 H를 각천의 그런 통수 능력으로 봤을 때 결과값이 범람이 일어나면 안 돼요.
아웃풋 is flooding or not? flooding. 오케이.
그리고 세 번째 시스템 아이덴티피케이션은 그 터널 정기 규정으로 그 안반의 막장 후에 그 안반을 평가하는 거. 그거는 인풋을 이렇게 웨이브로 잡고 아웃풋을 레지스턴트로 잡아서 시스템의 락 컨디션을 평가하는 거잖아요. 디컨볼루션 프로블럼은 그 함수비 크게 함수비 측정으로 해서 X를 함수비로 잡고 H를 소열 시스템에 넣고 Y를 이제 모든 그 중량의 변화를 가지고 함수비를
오케이. 맞는 거 같니? 응, 맞는 것 같습니다. sounds about right. Okay, next group.
저희는 시장비인데 제가 본인이다 보니까 군 관련된 부분이 나왔는데 첫 번째 시스템 비전 프로그램은 인풋은 이제 저희가 갖고 있는 경력과 장비가 있고 결국에 저희가 승리를 해야 됩니다. 그러려면은 훈련 시스템이라든지 또 지금 현실한테 과학과 시스템을 이용한 훈련을 하고 있기 때문에
그렇습니다.
계속 대화를 하고 체계를 하는
네.
것도
네.
시스템 디자인이라고 할 수 있을 것 같습니다.
맞는 것 같습니다. 네. convolution problem.
컨버전은 뽑기를 생각했습니다. 돈 넣고 시스템이 돌아가면은 뭔가가 나옵니다. 로또 생각하시면은
로터리 시스템.
돈이 있으시고
돈이
이렇게 번호로 돌아가는 시스템을 거치면 결과가 나옵니다.
네. 오케이. next. system identification.
시스템 아이덴티피케이션은 이순례 교수님 연구소 같이 하고 있는 어떤 상사태 토속류 연구가 될 수 있는데 결국 이제 어떤 집안 특성이랑 이런 게 이제 인풋이 되고 결국에 이제 데브리 플로우가 발생을 하는데 그 과정을 이제 그거를 확인하기 위한 시스템들이 있지만 그게 어떤 식으로 과정을 통해서 토속류로 발전하고 하는 시스템을 저희가 개발하고 연구하는 게 이제 시스템 아이덴티피케이션이라고 생각했고 마지막 거
Deconvolution.
도 약간 돈 관련된 거긴 한데 그 대포병 레이더가 있습니다. 그러니까 대포병인데
네.
적이 저희한테 탄차를 쏩니다. 그러면은 그 탄착이 떨어지는 데를 이용해서 역으로
네.
적의
source를, location.
적이 쏜 위치를 확인하는 레이더가 현재 지금 티벳에 자주 등장하는데 백령도에 같은 데서 유명하고 있다고.
네.
그런
that's
레이더가 결국
that's a great example of deconvolution problem. Okay. Good. Great. Okay. Next group. Last one. System design. Okay. Okay, frequency response is the response and output. Shape of object. Okay. Deconvolution problem. Criminal. That's a good example. think the forensic analysis is also a good example of the deconvolution problem. Good, great. I think so. Depending on the known and unknown, actually, you can use just one example, one case to be a forward problem, inverse problem, or system education, convolution, and deconvolution, everything. For example, if we do the triaxial test, you want to find the phi and C, the cohesion, right? Cohesion of the soil, right? Then, is it forward problem or backward problem? Or system identification? System identification. It sounds like material property determination can be considered as the system identification. So you are going to find out, or you want to understand the system, right? And from the CMP, right? Strength parameter. What else? The forward problem is. And then you perform the triaxial test with the known soil, and you want to find the stress strain response. That's convolution problem, is it? The system is known, the soil is known, and you know the loading. The loading will be the input, so that the loading deformation curve is the output, and that's the answer that you want to find. Right? Backward problem is what? You don't know the loading, or you don't know the loading rate, and you have the output, response, and you find out what's the confining stress from the output. Then that's the convolution problem, the deconvolution problem, right? So using the one case, you can make the examples. Okay, great. So I think you guys have a concept about this signal and the systems, and examples of signals and system time and spatial variation in one dimension. I think you can read it. So for example, here, chemistry, the material science, the temperature history in the chemical reaction. So temperature varies with time only. So one-dimensional variation. And two-dimensional spatial variation is like topography, right? And three-dimensional variation is porous network in particulate medium. Is like you have a porous network in X, Y, Z. So that's why they call it 3D. And what else? Pore pressure underneath a dam. So then you have a dam structure, and along the area and also along the depths, you have a pore pressure distribution. So that's a three-dimensional information. So then we'll talk about the system. We have an active system, passive system, and feedback system, or the self-controlling system. An active system is what? It's like a bat and dolphin. So they have their own energy to propagate the signals, right? So bat and dolphin use the ultrasonic frequency to detect some obstacle in front of them, right? And they use the sweeping signal. And in civil engineering, we have a impact hammer test, and using the geophone, we find out the anomaly in the subsurface. Right? So then this is another active system, example of the active system. So that's what, and because we will have to apply the mechanical energy to generate the signal. Ground penetrating radar, high resolution, these are the same thing. And passive system. So you don't need the extra battery or the external energy to generate the signal. So the system itself has the natural or ambient signal generating from itself. The stethoscope, right, 청진기, or electrocardiogram for kidney. So it just measures the resistance, right, of your body, because your body also generates some current. Right? And accelerometer. Actually, it's different. Actually, it's not accelerometer. It has to be piezo, I think. So when you have a movement, piezo itself generates the mechanical, the electrical energy. So it doesn't need the extra current or the extra input voltage to generate the response. Or the self-calibrating system or the feedback system is that you use the output signal as your input. Okay? So then it's called the feedback system. I think this is not very relevant to our subject, but it just shows the example of the signal. This is the soil S-wave curve. I think from here, this is just a noise. And at the 78 kilopascal to the 800 kilopascal, as you increase the effective stress above the soil, the S-wave velocity increases. And when you unload it from the 800 kilopascal to the 0, it goes back. So that means the velocity, arrival time gets delayed, so the velocity is getting slowed. Right? Signal processing, I think. So, I think when is it? For like a month later? Yeah, 5th week and the 6th week, we'll talk about the time domain signal analysis and the frequency domain signal analysis. And also we'll talk about the noise. And the signal and noise, difference between signal and noise is signal is the information that we want, and noise is the all kinds of other signal that's not wanted. Right? So then the key of the signal processing is to reduce this noise and to get and also highlight or to embrace the signal that you want to measure. Oh, this is the example of the deconvolution. Here is the forensic engineering, as Hyun said. Gunman location from sound recordings in newscasts could be an example of the deconvolution. And system identification, I think you guys can go through it. And one maybe astronomy, origin of the universe from the rate of expansion and the redshift. So summary. Let's read through it. Signal characterization, decoding, interpretation are important components of engineering practice and research. There are 4 problems and inverse problem. The revolution in computer technology and digital electronics has led to the development of devices and procedures that operate on discrete signals and to the solution of forward and inverse problems that are stated in discrete form. Today, discrete signal processing and inverse problem solving technique impacts all aspects of daily life with countless examples in engineering science. So we'll talk about the discrete signal processing a little bit in this class, and then we'll talk about the elastic wave in soil and the electromagnetic property and electromagnetic wave propagation in soil.